Hi everyone, let me introduce myself. My name is Ramirez Arenas Marco Arturo, and my team is conformed by Noriega Huerta Alan, Soto Piñeiro Abril, Cabrero Juárez Leonardo, and Trinidad Chavarria Roberto Carlos. My team is in charge of presenting the topic about the transformation of solar energy before and after it joins the Earth. To understand this topic, we are going to divide it in 3 steps. The first step consists about the nuclear reactions that happen in the core of the Sun, and the journey to Earth that the photons it produces. The second is about the process in which the solar energy goes through the atmosphere of the Earth. And the third step is about the type of energy in which the solar energy is used after it enters the Earth. I am the one in charge of introducing you to the topic. So let's go to the first step and let's talk about the Sun. The Sun is the star of our solar system, and it is the one in charge of providing us of light and energy. But how does the Sun produce this energy? Well, at the beginning of the century, the mechanism that kept the star shining was an enigma. It was until the discovery of the equivalence between mass and energy of Einstein, E equals mc squared, that it was determined that by nuclear fusion of a conversion of particles of hydrogen and helium, that it was possible to generate enough energy to keep the Sun warm for more than 10,000 millions of years. And actually, the Sun is at the half of its life. It is about 5,000 millions of years. It has a lot of life left, right? And what is the nature of these fusion reactions? The kind of fusion reactions that are given in the interior of the Sun are so different than the ones that can be made in a laboratory. To begin with, the initial fuel of a star like the Sun is essentially made by nucleus of hydrogen. This means protons, and in some way the nature has to combine 4 protons to form helium. This can be made by 2 mechanisms. One is a proton-proton chain, and the other one is the carbon cycle. But in the case of the Sun, the dominant mechanism to generate energy is the proton-proton chain, so let's focus on that. This mechanism starts when 2 protons fuse each other to form deuterium, an stable isotope of hydrogen. In this reaction is released a positron and a neutrino. This is the result of the beta decay of a proton to a neutron. Once the deuterium is made, it can react with another proton to make a light isotope of helium, accompanied with an emission of gamma ray photons. At this moment, 4 reactions can happen, but one of them happens 91% of the time. So let's focus on this one. In this reaction, the isotope of helium that was made reacts with another isotope of helium of the same characteristics. So this will mean that we will have 6 protons, and the result will be that 4 protons fuse each other to form a greater isotope of helium, and the other 2 protons can be used to start the cycle again. This way, the mechanism starts over and over and over again, producing energy for a lot of time.
To continue, I'm gonna talk about the random trip that photons made from the Sun's core to the Earth's atmosphere. So, as we may know, it takes light and 8 CP minutes to reach us from the surface of the Sun. So, how long do you think light travels from the Sun's core to its own surface? Seconds or maybe a minute? Well, the answer is many thousands of years, and I'm gonna explain why. Photons are produced by the nuclear reactions deep in the core of our Sun. As they flow out of the core, they interact with matter and lose energy, becoming longer wavelength forms of light. They start out as gamma rays in the core but end up as X-rays, ultraviolet, or visible light as they near the surface. However, that journey is neither simple nor direct. Upon being born, each photon travels at a speed of 300,000 kilometers per second until it collides with a proton and it is diverted in another direction, acting like a bullet ricocheting off of every charged particle it strikes. The question of how far this photon gets from the center of the Sun after each collision is known as the random walk problem. The answer is given by this formula. Distance equals step size times the square root of the number of steps. So if you were taking a random walk from your front door with a 1 meter stride each second, it would take you 1,000,000 steps and 11 days just to travel 1 kilometer. So then, how long does it take for a photon generated in the center of the Sun to reach you? We know the mass of the Sun and can use that to calculate the number of protons within it. Let's assume for a second that all the Sun's protons are evenly spread out, making the average distance between them about 1 times 10 to the negative 10 power meters. To random walk the 690,000 kilometers from the core to the solar surface would then require 3.9 times to the 37 power steps, giving a total travel time of 400 billion years. That can be right. The Sun is only 4.6 billion years old. So what went wrong? Two things. The Sun is not actually of uniform density, and photons will miss quite a few protons between every collision. In actuality, a photon's energy, which changes over the course of its journey, determines how likely it is to interact with a proton. On the density equation, our models show that the Sun has a hot core, where the fusion reactions occur. Surrounding that is the radiative zone, followed by the convective zone, which extends all the way to the surface. The material in the core is much denser than lead, while the hot plasma near the surface is 1,000,000 times less dense, with a continuum of densities in between. And here's the photon-energy relationship. For a photon that carries a small amount of energy, a proton is effectively huge, and it's much more likely to cause the photon to ricochet. And for a high-energy photon, the opposite is true. Protons are effectively tiny. Photons start off at very high energies compared to when they are finally radiated from the Sun's surface. Now, when we use a computer and a sophisticated solar interior model to calculate the random walk equation with these changing quantities, it results of 170,000 years. Future discoveries about the Sun may refine this number further, but for now, to the best of our understanding, the light that's hitting your eyes today spent 170,000 years pinballing its way towards the Sun's surface, plus 8 minuscule minutes in space. Meaning that the light we receive takes 170,000 years to get through us. Thank you.
We're going to talk about atmospheric effects. Atmospheric effects have various impacts on solar radiation on Earth's surface. The main effects for photovoltaic applications are four. The first one is a reduction in the power of solar radiation due to absorption, scattering, and reflection in the atmosphere. The second one is a change in the spectral content of solar radiation due to the increased absorption or scattering of some wavelengths. The other is the introduction of a diffuse or indirect component to solar radiation. And the last one is local variations in the atmosphere, such as vapor, water vapor, clouds, and pollution, that have additional effects on incident power, spectrum, and directionality. The subtopic is absorption in the atmosphere. As solar radiation passes through the atmosphere, gases, dust, and aerosols absorb the incident photons. Specific gases, particularly ozone O3, carbon dioxide, CO2, and water vapor H2O, have very high absorption of photons that have energies close to the binding energies of these atmospheric gases. This absorption produces deep valleys in the spectral radiation curve. For example, much of the far infrared light above 2 micrometers is absorbed by water vapor and carbon dioxide. Similarly, most of the ultraviolet light below 0.3 micrometers is absorbed by the ozone layer, while absorption by specific gases in the atmosphere changes the spectral content of terrestrial solar radiation. They have a relatively minor impact on total power. Instead, the main factor in reducing the power of solar radiation is the absorption and scattering of light due to air and dust molecules. This process does not produce the deep depressions in spectral irradiation, but rather causes a reduction in power depending on the length of the path through the atmosphere. When the sun is above, the absorption due to these atmospheric elements causes a relatively uniform reduction throughout the visible spectrum, making the incident light appear white. However, for longer path lengths, higher energy, shorter wavelength, light is more effectively absorbed and scattered. Therefore, in the morning and in the afternoon, the sun appears much redder and has a lower intensity than in the middle of the day. Another subtopic is direct and diffuse radiation due to incident light scattering. It's absorbed as it passes through the atmosphere and at the same time is subject to scattering. One of the mechanisms of light scattering in the atmosphere is known as Rayleigh scattering, which is caused by molecules in the atmosphere. Rayleigh scattering is particularly effective for short wavelength light, which is blue light, since it has a lambda minus 4 depends. In addition to Rayleigh scattering, aerosols and dust particles contribute to the scattering of incident light, known as Mie scattering. The scattered light is not directed and therefore appears to come from any region of the sky. This light is called diffuse, since diffuse light is primarily blue light that comes from regions of the sky other than where the sun appears blue. In the absence of scattering in the atmosphere, the sky appears black, and the sun would appear as a source of disco light. On a clear day, about 10% of the total incident solar radiation is diffuse. As a final subtopic is effect of clouds and other local variations in the atmosphere. The final effect of the atmosphere on incident solar radiation is due to local variation in the atmospheres. Depending on the type of cloud cover, the incident power is dramatically reduced.
Well, good morning. I'm going to talk about the passive solar energy. It is the set of techniques aimed at harnessing solar energy directly, without transforming to another type of energy, for immediate use of the storage without the need for mechanic system or external energy supply. Also, it can be complete by them, for example, for its regulation. Technologies that use pumps or fans consume a significant amount of energy for their operation and therefore are classified within active solar technologies. Some passive solar systems may, however, consume a small amount of energy needed to activate gates, relays, switches, or another device that will improve the performance of this system in the collection, storage, and use of solar energy. The applications, it can be thermofusion, base water heating systems. Autonomous solar heater work for the same effect. When the water in the collector warms up, it rises to the tank, located at its highest part. If water in the tank is cooler, it descends through another conduit to the bottom of the collector. Solar stops. The benefits is about the passive solar systems are characterized by requiring little or not cost to perform their work, very low for their maintenance, and do not emit greenhouse gases during the operation. The thermal solar energy. The thermal solar energy consists of the transformation of solar energy into thermal energy. It is a form of renewable energy, sustainable and respectful with the environment. This way of generating energy can be applied in homes and small installations and in large power plants. There are three types of solar thermal energy. For example, high temperature solar thermal power plants, generation of electricity. They work with temperatures above 500 degrees. The medium temperature, they use devices that concentrate solar radiation to obtain higher temperatures between 100 and 300 degrees. The low temperature, it could be the case of installation in houses. In this case, thermal energy is used directly. They work with temperatures below 65 degrees. The solar collectors. A solar collector is a type of a panel for thermal solar energy. They are also called a solar collector. The collectors transform solar energy into thermal energy. In solar thermal power plants, solar radiation concentrate at one point to generate steam. With the steam, a steam turbine is powered with you get a mechanical job, and finally the turbine is connected to an electric generator. The operation of solar thermal power plant is very similar to a coal or nuclear thermal power plant. The difference is the way of generating heat to obtain steam. In thermal power plant, the heat comes from the combustion of fossil fuels, and on the other hand, energy is obtained by fission of uranium. In our case, the initial energy is obtained from the sun. Thank you very much.
Hello, as my partner says, my name is Alan and I'm going to talk about photovoltaic solar energy and some derivatives. Photovoltaic solar energy is a source of energy that produces electricity of renewable origin, obtained directly from solar radiation by means of a semiconductor device called a photovoltaic cell, or by means of a deposition of metals on a substrate called a thin-film solar cell. This type of energy is mainly used to produce electricity on a large scale through distribution networks. It can also be used to power countless applications and autonomous devices, as well as to supply mountain shelters or houses isolated from the electricity grid. Applications of photovoltaic solar energy. Telecommunications and signaling. Photovoltaic solar energy is ideal for telecommunications applications, including, for example, local telephone exchanges, radio and television antennas, microwave relay station, and other types of electronic communication links. Another one is isolated devices. The reduction in the energy consumption of integrated circuits made it possible in the late 1970s to use solar cell as a source of electricity in calculators,
such as the Royal Solar One, Sharp EL8026, or Teal Photon. Rural electrification in insulated environments where little electrical power is required and grid access in difficult photovoltaic panels have been used as an economically viable alternative for decades. Pumping systems. The photovoltaics are also used to power pumping installations for irrigation systems, drinking water in rural areas, and watering holes for livestock. 777 and 8 or water desalination systems. Solar diesel hybrid systems. Due to the falling cost of photovoltaic solar energy, the use of hybrid solar diesel system is also spreading, combining this energy with diesel generators to produce electricity in continuous and stable manner. Another one is transport and maritime navigations. Although photovoltaics are not yet widely used to provide traction in transport, they are increasingly being used to provide auxiliary power in boats and cars. Many photovoltaic systems are often located on buildings. They are usually placed on an existing roof or integrated into elements of the building structure itself, such as skylights or facades. One of the main applications of photovoltaic solar energy that has been most developed in recent years consists of power plants connected to the grid for electricity supply. 103, as well as photovoltaic self-consumption systems, which are generally smaller in power but equally connected to the electricity grid. Although solar panels are usually installed on land, it is possible to install them floating on water from reservoirs or quiet lakes. The environmental benefit. The amount of solar energy reaching the Earth's surface is enormous, about 122 petawatts, and is almost 10,000 times more than the 13 terawatts consumed by the humanity in 2005. This abundance suggests that it will not be long before solar energy becomes the main source of energy for humanity. Hybrid solar energy. Hybrid solar power system is a system that combines solar energy using photovoltaic system and with another energy source. A common example is a hybrid diesel photovoltaic system combining photovoltaic energy with diesel generators. Another system is hybrid wind and solar system. The combination of wind and solar photovoltaic sources has the advantage that the two sources complement each other, because the peak operating times of each system occurred at different times of the day or year. After this explanation, I leave you a little video. Enjoy it.
So you're ready to switch to solar, but you're not sure what kind of system to get. Wholesale Solar offers a variety of systems to meet every need. Let's look at the different types. The first is the grid-tied system for anyone connected to the local power grid. This system uses solar panels connected directly to the power grid and lets you actually sell the power your system generates to offset your energy costs. Grid-tied systems are the cheapest option and offer the fastest payback and best return on investment, and are ideal for anyone trying to save money on their power costs. An off-grid system uses solar panels to charge a bank of batteries. The batteries then power your home. Smaller versions of this system with specially flexible panels can be used to power recreational vehicles or boats as well. Off-grid systems are ideal for remote areas, undeveloped land, and anyone with no access to utility power. These have a higher system cost because of the addition of the batteries, but can also let you access more affordable land. With an off-grid system, energy conservation is important, so energy-efficient appliances and a backup generator are essential. The best of both worlds is a grid-tied system with battery backup, which is ideal for anyone with unreliable power and critical appliances, like a water pump, lights, or security system. It's also more expensive than a standard grid-tied system and has lower return on investment. With this system, the solar panels send power into the grid for credit when it's available, and batteries power some appliances during an emergency outage. Remote industrial power systems are off-grid systems designed for powering remote equipment for a variety of different uses. These are essentially off-grid systems designed to run certain equipment that may include backup generators or wind turbines. There are also battery backup systems which are only recharged by the grid or a generator and don't have solar panels, commonly used for businesses that need emergency backup power for critical appliances. Whatever PV system works best for you, Wholesale Solar can help. To save yourself hours of tedious research, download our Getting Started guide to learn how to buy a solar energy system the right way.